Hi folks, thanks again for waiting. I wanted to re-record parts of this lecture because things were not exactly totally right in the live lecture. So I'm just going to start from the beginning. Then at some point I'm going to kick it over to me from yesterday and then I'll take it back from me. So far, what we've seen in class are two different implementation approaches for sets and maps. So for sets and maps, we've had a tree-based approach. That would be like a binary search tree or a 2-3 tree or a red-black tree. And the actual tree map and tree set that Java uses are the red-black tree that we described. Slight tweaks, but same core idea. These approaches, the tree-based approaches, required that our items could be compared because we have to have a notion of less than to say that all the items left are less. And we also found that the operations were, worst case, log time. What we saw in the last lecture was how we can use a hash table based approach to create a hash set or hash map. And with this approach, we don't have to have our items comparable. They could be anything. And we get constant time operations so long as the hash code spreads the items out nicely. So we've got the basics done so far, but what I want to do in this lecture is reinforce these ideas. We only got one lecture to look at them. And so I'm going to start by just recapping exactly what a hash table was, and then tell you what I want you to get out of today. Okay? So recall that with a hash table, the idea is that for any piece of data, like a string or anything else that we want to store in a hash table, or a hash set, we could say, as an example, we convert that data into an integer. And the integer is anywhere between -2 billion and 2 billion, all the space of all possible Java integers. And once I have that number, I need to convert that number into a bucket number, which is which of the many linked lists I want to use. And so I will use, as I described in our implementation for our class, the floor mod function, which is what you think of as modulus. So this right here, if I mod this by 4, I get 0. And so I would use the 0th bucket to store this string in Vietnamese. Okay, that's the basic idea. Now, each of the buckets that I get are sometimes called a separate chain of items because you can think of them as a bunch of separate linked lists. And the job of the hash table is basically just to dispatch queries to each of those linked lists and hopefully get better performance by having many linked lists. Now, we saw last time, we have a variable number of linked lists, and the idea is that we resize that array of linked lists whenever the load factor exceeds some constant. So we could pick any number, 2, 5, as we'll see later, Java picks 0.75. And so long as the items are spread out nicely between the buckets, we'll get constant runtime on average. And the reason it's constant on average is that if the items are evenly distributed, all those lists are short. So for example, if I pick a load factor of 3 and the items are evenly distributed, then we're going to have exactly 3 items per bucket. And that's going to be very fast to look at. All we do is we take the data, compute which of the buckets it's in, and then there's only 3 items in the bucket. So that's constant time to look through a list of 3 things. Okay. So as long as you're resizing and making sure you have a lot of buckets and then you have items evenly spread, we will get constant time operations on average. Now, if we don't have resizing, say we only have 7 lists and that's it, it'll be linear time. You could say the overall runtime will be n over 7, but in the large n limit, that 7 doesn't really matter. I mean, it helps, but it doesn't get you to constant time. Okay, so the whole trick is we have a bunch of lists that are all short. Okay, and we're going to see some visualizations throughout the day, and we'll see by the end what Java's hash set, how it feels, and we'll see, okay, it's always going to be around 5 items at worst, at least for the numbers I pick, and that's not so bad. Okay, turns out to be, well, never mind, I'm not going to go into it now. Okay, so what we're going to do in the first part of this lecture is we're going to try, well, actually throughout all of it, is we're going to use the hash table visualizer that I built. And it's going to show us a few things. 1, how do hash codes affect how items are distributed? 2, how are equals and hash code methods interrelated? And 3, we'll get a sense deeply of why hash tables are fast, even though they use linked lists, and we'll eventually dig into exactly how Java's hash set is implemented. So what I'm going to do is have a running demo where we're going to be inserting into a hash table objects of type colored number. Okay, a colored number has 2 attributes, a number, like 6 or 25, and a color. And we'll see that the colors, there's maybe, I forget if it's 5 or 6 choices, and the goal here is just to add some variety and give us some things that we can play around with, okay? So we're going to insert these colored numbers 0 through 19 into a hash table with 6 buckets, and we'll get something like this, okay? So I'm actually going to go to the live visualization, and I'm going to open up the right code, and I'm going to go to colored number, and I'm going to, actually I'm gonna go to hash table visualizer. Okay, that's the demo we're gonna do at the very end. Attentive viewers will see that I'm actually recording this one last. So what I'm gonna do here is, yeah, this all looks good to me. So I'm gonna run this code and see what happens. So I get here, as I'm inserting items, they're appearing effectively randomly throughout the hash set. Okay, that's how it looks. Okay. Now the demo I ran live in class, I had a different distribution than the one I have here, if you look carefully. So we'll focus on the one that I got here. They're very similar, but yeah, I'd like you to think about, what do we notice about this distribution of items? Do things land where you expect them to be? And why do we get this distribution and not some other? So think about that. Like, pause the video, but I really think this is worth thinking about. Okay. You can whisper the answers to yourself, or the wall, or your friend who you're watching with. Or if you have a dog, please speak to them about what you observe. Okay, so what do we notice about the distribution of items in the live lecture? People said it's pretty random. There's a fairly even distribution. Some of the rows seem a little longer than the others. There's more odd rows in the odd rows than the evens. I think that's just pure chance. And there's also noted that things are in weird places. So for example, why is 19 and 0? Or why is 1 and 3? Okay. Other question is, why do we get this specific distribution? Okay, well, I'm going to take over there. And the reason we get this specific distribution is that the default hash code is, I should say usually, just the address of the object. Okay. So whenever you create, example, when you create new colored number 2, it is going to allocate some memory and put it there. And then the hash code is just going to be some arbitrary number, some big number. And then that gets modded by 6, which in this case happened to be 0. Okay. And so why we see what is effectively totally random behavior is the fact that the hash code is, well, effectively totally random. So what I'm going to do now is toss it over to me from the live lecture yesterday and let him explain this bit.